Annenberg Media.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
what is ahead in the future for chemistry and for this society that is so affected by chemistry? Much excitement, deeper understanding, new molecules that no one has yet thought of. But one thing is not going to change. This science is done by people, people such as yourselves. Oh, they may have fancy titles, chief executive officer of this company, head scientist, professor, Nobel laureate. But behind these titles are just people, people obsessed by curiosity. Chemistry has been a democratizing force. It has brought a wider range of products to more people than could ever afford them before. Chemists care about their science and about their society. And so in this program, we brought some of those people together. They have some intriguing and dramatic opinions. And because I'm one of them, just a chemist, I'm going to join my friends in this half hour. We will look at the future as best we can. What lies in the years ahead is certain to exceed our vision.
Where I think chemistry is going is outwards in different directions. It's outwards towards the areas of biology, and those are the sorts of things that I'm involved in. It's outwards towards physics, towards the areas of engineering, towards the construction of different kinds of materials, and also towards the construction of different kinds of biopolymers.
So if I had a career plan that I wanted to be part of the 21st century shock troops that are attacking the major diseases of plants, of animals, and so on. I want to clean up toxic waste. I want to clean up the ocean. I want to get rid of AIDS. I want to get rid of I want to get rid of malaria, schistosomiasis, and so on. That's going to be accomplished by manipulating molecules. The chemists will be in the middle of it.
As they broaden their horizons and ours, chemists are linked to new instruments and techniques. For example, the latest electron microscopes image objects in ways impossible only a few years ago. Dr. Howard Schneiderman, Chief Scientist, Monsanto.
We have gotten to a point where we can see a molecule. We can see a molecule with a tunneling electron microscope, with a variety of techniques. We can see molecules.
Chemists can now probe the interior of molecules with lasers, and a hydrogen fluoride chemical laser may have future applications that its inventor never fully intended. Dr. George Pimentel.
It turned out to be a very effective and powerful laser, so powerful, in fact, that it was considered as a possible weapon, that is to say, a chemical reaction which could produce a light ray, a laser light ray, of sufficient intensity, sufficient power, to possibly do some damage.
And there are scanners in medical diagnosis using radioactive isotopes. Emissions map the functions of different organs, including the brain in action. Another application of this technique is in testing new drugs. Dr. Michael Welch.
If drug companies label the new drug with a positron-emitting radionuclide, administer it to patients or normals, they can find out the mode of action, they can find out how much concentrates in a particular part of the body, they can find out how long it stays in that part of the body, they can find out if it goes to a part of the body they don't expect it to go to.
And there are computers in chemistry. Computer graphics illuminate molecular architecture. They enhance innovation in design. Dr. Bertram Fraser Reed.
Imagine that you want to bring two bodies together, to fuse them together. Now, what is the best way to do that? Is it better that they come together in this way or in this way? What forces govern this choice versus this choice? A computer can tell you that because you can probably plot in the various things that favor coming together this way versus the things that favor coming together in this way.
Supermicroscopes, lasers, scanners, computers, and more. New technologies linked to chemistry. Chemistry is spreading outward, a vigorous new partner in other domains of science, like materials science. Dr. Frank DeSalvo.
We have to both make materials and look at their properties, which is the overlap between chemistry and physics, if you like. In order to do the kinds of things you want to do as a chemist or as a physicist, you have to have appreciation for what went into making the solid, or what I can do to the solid to change its properties, for example. So you need to understand both sides of the fence, and that's becoming a larger and larger requirement in the field of solid-state chemistry, solid-state physics. If you look at physics today, and you look at physicists and ask what they are doing, more than half of all physicists are working on materials. And that means that they're working on things that have to be made by chemists or someone, a material scientist, making materials. And they're trying to understand why these materials behave the way they behave. And so the overlap between chemistry and physics is already very large.
Keith McKinnon, President, Dow USA.
The new kinds of materials that are being developed have remarkable properties. I mean, they have thermal properties and tensile strength properties that are almost unbelievable in the context of the materials we are used to seeing. So for very sophisticated kinds of applications, and high-speed aircraft are an example of those, the so-called Orient Express and projects like that will, I think, find a use for those kinds of materials. The space program, as I'm sure people are aware, has been a major impetus in developing new materials and developing the whole field of material science. I believe that's going to continue, and that in the next century, as I say, we'll see materials that we can only imagine today.
Richard Heckert, Chairman, the DuPont Company.
We've discovered that you can fill polymer systems, even ceramics, with high modulus inorganic materials, carbon fiber, some organic materials too, things like our Kevlar or glass fiber or inorganic fibrids of various types from different minerals. Some of these old systems filled with those materials produce remarkable compositions that will do jobs that we never thought plastics capable of doing.
And then there are the superconducting materials. Their invention shows how a chart 100 years old will still have a great future 100 years hence.
The copper oxide superconductors are made by combining copper with oxygen. That bonding is rather covalent, making in just combining copper and oxygen, a binary compound that's not so interesting. But if I combine them further still with elements from the left-hand side of the periodic table, like lanthanum or strontium, I obtain interesting superconductors. That appears to come from the interplay between the ionic bonds that these materials want to have with oxygen and the covalent bonds that copper wants to have with oxygen. If you were to ask me to summarize on one sheet of paper all the potential things that could happen in chemistry, not only in chemistry, but in all fields of science, physical science that is, and maybe in engineering, the one sheet of paper I'd give you would be the periodic table. That's everything we ever will do in science is summarized here. All the compounds that we'll ever make will come just from combining these elements, these 100-odd elements on this one sheet of paper.
The periodic table was a product of basic research. Tomorrow, as today, there will be those who seek purely to acquire new knowledge for its own sake, with no regard to eventual application. Much fundamental research in the future will be done to create new molecules. Nobel laureate Roald Hoffmann.
People make molecules for all kinds of reasons. One of them is that a molecule is beautiful. That, for instance, is the case with this fantastic platonic polyhedron, as it's called, of dodecahedrane, with 20 carbon atoms in it, with 12 faces, all pentagons. This was made not too long ago by a friend of mine at Ohio State, Leo Paquette. Now, he made it because it was a goal, a mountain to be climbed. Many people had tried, no one had made it, and it's aesthetically pleasing in its symmetry.
Dr. Jacqueline Barton.
Now, where I think we're going is into bigger and, in some respects, more complicated structures. Those kinds of complicated structures allow us to design, in one respect, on a molecular level, macromolecular assemblies, multi-atom assemblies that have a particular material characteristic, a particular macroscopic characteristic. And yet what we're really doing is we're tailoring, we're designing that material on a molecular level.
You see this gracefully curving triple helix. Now, this structure has not been made. What I see is that it's pretty, it's beautiful, and it also has some interesting properties. So in a few months, we will publish something on this, and maybe someone will try to make it then.
Beyond basic research, the synthesis of new molecules will sometimes have enormously beneficial applications. Increasingly, chemistry will enter the domain of medical science.
The sophistication of drugs demands that we have a better and better understanding of biology, of biochemistry, how nature does things, because there's still so much to learn. I mean, my goodness, the thought of things that takes me years to do, nature does in a matter of seconds. The secrets there still have to be unraveled.
Unlocking those secrets will assist in the rational design of drugs.
Monoclonal antibodies are molecules that are specific, again, to proteins in the body, particularly to sites on tumors. That if one can label these antibodies with radioisotopes, one can either see where the tumor is or ultimately add a large amount of radioactivity to in fact kill the tumor by radiation therapy. This is in fact called the magic bullet way of killing tumors. If one could get most of the isotope to the tumor, it would perhaps be the ideal way of destroying tumors. Instead of irradiating from the outside of the body, as one does in conventional radiation therapy, one would only irradiate the tumor.
We've come to realize that drugs obviously need the right functional groups to attack the target in the body. They also have to fit the space available in attacking that target. The importance of shape as well as functionality is one that came to us fairly recently, I guess, not the last year, but in the last decade or so. The remarkable thing about the computer is it will enable us to display in 3 dimensions on on a video tube what a complicated molecule looks like. And it enables us to look at the pocket or target where we think a drug might be efficacious if it were supplied there. And then we can examine different compounds that are potentially useful in the treatment of this disease or attacking that target to see if they fit. Now, fit isn't everything, but if it doesn't fit, you probably don't have a decent treatment, a good drug.
If we can understand the way those proteins work, if we can understand the architecture associated with those proteins, then we can do things like design better drugs that target and recognize that architecture and interact with them. And that's really, in some respects, in my mind, the basis of new rational design of pharmaceuticals. That is, in developing any new pharmaceutical agent, what we have to do is either come up with a molecule that either recognizes the molecular architecture of a biopolymer or acts as a monkey wrench, if you will, for interfering with the chemical reaction that occurs on that biopolymer.
I think that it represents really the cutting edge of modern chemistry, trying to find mimics for peptides, mimics for proteins. No one has developed a very good technique for making a protein pill or a peptide pill. They get digested, proteins and peptides, in the stomach. It would be great if we could design a molecule that would do the same thing as insulin, but you wouldn't have to inject it. You could take it as a pill. People haven't found that molecule.
Chemistry may have an even greater effect on medical science and a host of other disciplines through the revolution in biotechnology, genetic engineering.
In some respects, you don't have to think about recombinant DNA technology as Woody Allen's world in Sleeper with oversized bananas and tomatoes. That's not what recombinant DNA technology is all about. What it is all about is our learning how to manipulate and change macromolecular structure, and in so doing, learn an awful lot more about that macromolecular structure and the chemistry that nature's been doing all the time.
Biotechnology is of interest to us because it is an extension of good, plain old organic chemistry, a very complicated extension of it. I think at this time it's particularly intriguing because we are beginning to understand life processes at the molecular level. We really know what's going on atom by atom, molecule by molecule. And at that point, the organic chemist has a perfect right to be a player on the team.
One of the really interesting questions is, what is the relationship between genetic engineering and chemistry? And I would argue that it's a very intimate relationship. It's manipulating molecules.
Chemists have a very important role to play in that particular area. That includes developments using recombinant techniques in the medical area. For example, hereditary diseases. It's going to be possible to understand which part of the gene is the part that's causing the problem and do repair work on it and perhaps thereby conquer the disease. Chemists will play a role in understanding just exactly what molecules are involved there.
In our early work with interleukin-2, which we thought had potential promise as a cancer treatment or at least as a pharmaceutical for related diseases, we were trying to isolate significant quantities of this material so that we could test it. It took us 6 months to isolate 10 milligrams from the conventional sources. Today, using recombinant DNA techniques, we can make that much in an afternoon at 1/1000th of the total cost of the old process. So clearly, this is a very powerful tool.
Biotechnology holds out the promise of engineering new molecules in the cells of plants as well as of people.
Among the specialty chemical areas that many of us think have a lot of promise are agricultural chemicals. Again, the world population continues to increase. There are many mouths to feed, will be many more. Efficiency and effectiveness in agricultural production is something the whole world is trying to achieve. Agricultural chemical products, I think, will play a big role in doing that. Both products as we think of them today and the new families of bioproducts, which I believe will be part of the agricultural business of tomorrow.
One can see the potentiality for deliberate engineering of the gene that determines the characteristics of the crop, whatever it be, whether it be a food crop and you wish to enhance the amount of growth, or perhaps a food crop that's susceptible to a particular insect pest or frost damage or whatever. One has at least the potentiality of reaching into the genes that are involved in the reproduction of that particular plant and engineering it to provide it protection or enhancement, whatever one wishes. That will involve some very sophisticated chemistry, biochemistry, and molecular biology.
We can produce plants which are resistant to diseases for which there is no known chemical that you can use to give those plants resistance. What are such diseases? Viral diseases, viruses. There is nothing you can spray on a crop that will eliminate viruses. But we can genetically engineer tomatoes and a variety of other crops so that they are resistant to not just one virus that normally attacks tomato mosaic virus. We can make those plants resistant to a whole string of viruses, a whole group of viruses. I think that within the next 5 years, there will be commercially in the marketplace a whole series of crops that are resistant to viral attack.
Agricultural products, drugs, superconductors, structural materials. Expanding avenues for 21st century chemistry. But what of the polymers and plastics we so take for granted today?
I suspect we'll be still making ethylene and propylene and polyvinyl chloride and all the traditional materials. The businesses that DuPont is in today, I expect, at least all the good ones, I expect us to be in at the year 2000 and the year 2010.
So chemists and the chemical industry will continue doing what they've always done, designing and producing new molecules that enrich the lives of us all. But at the same time, they are assuming new responsibilities.
One of the most important challenges that the industry faces is to make its products for society without in any way degrading the environment. We have made some mistakes in the past. Most of those mistakes were unintentional. They were simply based on lack of understanding. As we began to fully understand how persistent these byproducts, even some products, were in the environment, and recognized that some of them at least were probably undesirable and should not be there, we began a very broad effort to correct this problem. Our products are now being designed to be environmentally acceptable. Our waste streams are being minimized in every conceivable way, and this is a benefit to cost as well as to the environment. We're looking for new ways to recover small amounts of contaminants from drinking water and other parts of the environment that need cleaning up. In the long run, chemistry was going to tidy up its own nest, and someday we'll win back that approval that we so much desire from the general public.
All of my colleagues in chemistry, my colleagues in biochemistry, molecular biology, they must devote more of their energy and learn to communicate with the public. Not just the government, certainly including the government, but the public at large. And this is something that we have been reluctant to do. Far too few of us have actually been willing to come out of the laboratory and take on this very difficult task. But we must do it, not in the interests of chemistry, but in the interests of society.
Chemists and chemistry, then, will play new roles in the decades ahead. The people who do the science and the people who direct the industry are confident in their reach.
Chemists are involved in everything. There is no limit. And that's finally recognized, and everybody's having fun doing things they used to think were out of bounds.
The number of compounds that could be made potentially out of this are practically countless. We now know of maybe 10 million compounds, but with only perhaps 5 elements, thinking of the ways we could combine them, we could potentially make 10 billion compounds. So if we were to combine many, many elements from the periodic table, the number becomes absolutely enormous.
Look at what nature has done with a tetrahedrocarbon atom. It's built up all these molecules in life. There is an infinity of molecules based on the tetrahedrocarbon atom that are still waiting to be made.
Right now, today, is the most exciting time that I've ever seen for chemistry and for the chemical industry. I think we have more opportunities, more exciting horizons, more contributions to make to humankind, and more capability to make those contributions than at any time in the 30 years or so that I've been part of this business. And I'm really looking forward to see how all that turns out.
Annenberg Media.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.